Jai Hind everyone. My name is Manoj Kumar, Assistant Professor, Department of Computer Science and Engineering, Ajay Kumar Garg, Engineering College, Ghaziabad. Today, in this video lecture, we will discuss about the AVL tree in data structure. So, this will be the table of content. What is AVL tree? First, we will see the introduction of AVL tree. After that, different rotations in AVL tree, and next the insertion in AVL tree, and some problems of related to the AVL tree construction. So, let's start with the introduction of an AVL tree. So, AVL tree is basically a binary search tree, but it is a height balance tree. It means AVL tree follow the all the properties of binary tree, and extra feature is that height of the tree must be balanced. So, AVL tree is a binary tree in which the difference of height of left and right subtree of a node should be less than or equal to 1. Okay. Suppose, for example, this is a binary search tree. This is B, and left child of B is A, and right child of B is C. So, height balance factor of A is 0, balance factor of C is 0, balance factor of B is also 0. We will discuss here what is the balance factor. So, balance factor of a node is the difference between the height of left subtree and the right subtree. So, actually, in case of AVL tree, at first we have to calculate the balance factor of each node, and a formula to calculate the balance factor of each node is the height of its left subtree minus height of its right subtree. So, the left subtree of node B is A, so 1, and this is also 1, so 1 minus 1 is 0. So, again balance factor of B is 0. A has no left child, no right child, so balance factor of it is 0. Similarly, C has no left child and no right child, so balance factor of C will also be 0. Let us take another example. So, this is a height balance tree. If the balance factor of a particular node is 0, 1 or minus 1, then we can say that particular tree is balanced. If it is greater than 1 or it is less than minus 1, like it is minus 2 or 2, then in that case the tree will not be balanced. So, this is the example of balanced binary search tree or an AVL tree. Now, let us see this example. Here in this example, the right child of node C is B, and right child of node C, left child of node C is B, and left child of node B is A. There is no right child of node C. So, here since this particular node A, so what will be the balance factor of node A? There is no left child, no right child, so balance factor of node A will be 0. Now, balance factor of node B will be, it has one left child A, no right child, so the balance factor of B will be 1. Again, for node C, so balance factor of C will be the height of its left subtree minus height of its right subtree. In left subtree there are two labels, 1, 2. So, height of left subtree of C is 2, and since there is no right child of the C, so here the balance factor of C will be the height of left subtree 2 minus 0. So, balance factor of C will be 2. Again, this is another, so this tree is not an AVL tree. This is not height balance, okay, because the balance factor of node C is greater than 1. Here, in this case, the balance factor, there is no left child of A, and right child of A is B, and right child of C is B is C. So, balance factor of C is 0, and again balance factor of B is this will be minus 1, because there is no left child, and so balance factor of B will be minus 1, and again this will be minus 2, because their height of left subtree is 0 and height of right subtree is 1, level 1 and 2. So, 0 minus 2. So, balance factor of this will be minus 2. So, this is again a not an AVL tree. Different type of rotation. So, what is why we need different type of rotation in AVL tree? Actually, what happen when we construct an AVL tree, also in order to construct an AVL tree, when we insert a particular node or particular key in that tree, then it become unbalanced. So, whenever due to the insertion or due to the deletion, the tree become unbalanced, then to make that particular unbalanced tree balance or to make that particular unbalanced tree as an AVL tree, we need to perform some rotations. So rotations are required in AVL tree to make it balance. Okay, there are 4 type of rotation: left rotation, right rotation, left right rotation, and right left rotation. Let us see one by one to each rotation. So left rotation, what happen in case of left rotation? If a tree become unbalanced when a node is inserted into the right subtree of the right subtree, then we perform a single left rotation. It means whenever a tree become unbalanced after inserting a node in the right of its subtree, then we need to perform the left rotation. Actually, here the important point is that we need to recognize that when we have to perform which rotation to make the tree balance. So left rotation is required whenever a tree become unbalanced after inserting a node into right subtree of its. Okay, like here this is a particular node A. Now balance factor of A is 0 because for this no left no right. Now we insert B in the right. Okay, so balance factor of B will be 0 and balance factor of A now will be -1. So this is balanced till now. Now we have to insert C. Since C is greater than order of C is greater than A and B or also greater than B, so C will be inserted into the right. Okay, so here the balance factor, now here the balance factor of C is 0, balance factor of B is -1 and balance factor of A is -2 because left height subtree height is 0 and right subtree height is 2. So 0 minus 2, it will be -2. Now this tree become unbalanced. When it become unbalanced, when we insert C is what? Where the C is inserted? C is inserted in the right of A, in the right subtree of A. Okay, so in this case we need to perform the left rotation. And what we will do left rotation? We rotate the tree in anti-clockwise direction. So after performing the left rotation, this A will become the left child of B and C remain as same and B will be the parent. Now the balance factor of is 0, balance factor of C is 0 and balance factor of B is also 0. So this is the balanced tree. So this become unbalanced, and to make this balance we need to perform the left rotation. We will rotate the tree in the anti-clockwise direction and now it become balanced. Second one is the right rotation. Whenever we need to perform the right rotation. So if an AVL tree become unbalanced, if a node is inserted in the left subtree of the left subtree, then we need to perform the right rotation. Suppose we have a node, particular node C. Okay, now the balance factor of C is 0 because no left, no right. Now we have to insert B. Since the order of B is less than C, so it will be inserted in the left. Okay, now in this case the balance factor of B is 0 and balance factor of C become 1 because there is 1 left and no right. So 1 minus 0, 1. Now we have to insert A. So in this case order of A is less than B, so it will be inserted in the left side of B. So now this become balance factor of A will be 0 because no left, no right. Balance factor of B become 1 because 1 is left and no right. Balance factor of C become 2 because in left subtree height will be 2 and no right subtree. Okay, so now this become tree unbalanced. When it become unbalanced, because when we insert the node A and no node A is inserted in the left subtree of C. So in balance factor of this is balance factor of A is 0, it is okay. Balance factor of B is 0, it is okay. But the balance factor of C is 2, which is not acceptable. So we will see in context to C. So in context to C, A is inserted in the right of its right subtree. Its right subtree is B and A is inserted in the right of B. So here we need to perform the right rotation. And in case of right rotation, we will rotate the tree in clockwise direction like this. So what will happen? Here now B become the parent, A become the left child and C become the right child. A will be the left child. So 0, balance factor of A is 0, balance factor of C is 0 and balance factor of B is 1 or -1. So it will also be 0. So now it become balanced. So this will be the right rotation. Next we will see the left right rotation. Left right rotation is basically a combination of two rotation. Left rotation followed by the left rotation followed by right rotation. Okay, so here in this case, at first we have to make the tree balance. At first we have to perform the left rotation, and after that we have to perform the right rotation to make the tree balance. So wherever we require the need of left right rotation, so if a node has been inserted in the right or right subtree of the left subtree of a particular node and tree become unbalanced due to this insertion, then we need to perform the left right rotation. Let us see an example. Suppose this is a particular tree, we have a node C. Okay, so balance factor of C is 0. Now we insert A. Since order of A is less than C, so A will be inserted in the left. Okay, now we have to insert B. Now order of B is less than C, so it will become in the left subtree of C. Again we will compare here, order of B is greater than A, so it will inserted in the right of A as per the binary search tree property. So after inserting the A and B, this will become the tree. Now the balance factor of B is 0. Balance factor of A is there is no left child, so it will be 1, and balance factor of C is this is the left subtree of C. Okay, so label is 1 and 2 and no right subtree of C. So 2 minus 0, it will be C. So now the balance factor of C is 2. So this become unbalanced. Now in this case, if we want to make this particular tree is balanced, then we need to perform the left right rotation, because it become unbalanced when we have insert node B in the right of left of C. Okay, so what we will do in this case, first we rotate the tree with respect to A in the left direction. We will perform the left rotation first. Okay, so when we perform the left rotation in context to A, then A will become down and B will become the parent and C. Okay, this is also unbalanced. Now to make it balanced, we need to perform the right rotation. So when we will perform the right rotation, then C will become down and B will be the parent of the tree, and this will be the final tree. Now this is the balanced tree. Okay, next rotation is right left rotation. Right left rotation basically consists two rotation. At first we will perform the right rotation, and after that we need to perform the left rotation to make the tree balance. And wherever it is required, so if a node has been inserted in the left or left subtree of a right subtree of a particular node and tree become unbalanced, so to make that particular tree balance, we need to perform the right left rotation. For let us see an example. Suppose there is a particular node A. Okay, now we have to insert C. Since order of C is greater than A, so it will inserted in the right of A. Okay, now we have to insert the node B. Now we will compare here. Since order of B is greater than A, so it will inserted in the right of A. Again when we will compare here, since order of B is less than C, so it will be inserted in the left of C. So overall this balance factor of B is 0, balance factor of C is 1, balance factor of A of is 2. Okay, so now balance factor of A is 2, so it become unbalanced. So it become unbalanced when we insert node B in the left of its right subtree. Again C is in the right direction, so in the right subtree of a particular node. The insert node is inserted, yani it means B is inserted in the left of right subtree of a particular node. C belongs to in the right subtree and B belongs to left. Okay, so here we need to perform the right left rotation. So at first we need to perform the right rotation. So when we will perform the right rotation, we will rotate the tree with respect to C in clockwise direction. So it become like this. Again it is unbalanced. Now to make it balanced, finally we will perform the left rotation and we will rotate the tree in left direction. So this will be the final tree and this will be the this is a balanced tree. So here we perform the right left rotation. Now insertion in AVL tree. It means here some problem asked to construct an AVL tree. We have given some sequences of keys and we have to construct the AVL tree. Okay, so the first let us see an example here. In this example we have given some values or key sequence 14, 8, 12, 46, 23, 5, 77, 88, 20. Now we have to construct an AVL tree. So let us see step 1. First, insert a new element into AVL tree using the binary search tree concept. Okay, so in order to insert a new key or new element in an AVL tree, we need to follow the insertion rule of binary search tree. So first key will always work as the root of the tree. So first key is 14. So 14 is become the root of the tree. Now the balance factor of 14 is 0. Now we have to insert next 8. Since 8 is less than 40, so as per the binary search tree insertion, 8 will be inserted in the left of 14. So again this will be the tree after inserting the 8. Now balance factor of 8 will be 0 and balance factor of 14 will be 1. Okay, so this is balance. Now we have to insert 12. So when we will insert 12, again 12 is less than 14, so it will be inserted in the left subtree of 12. Now when we will compare here 12 is greater than 8, so it will be inserted in the right of 8. Again, now we will calculate the balance factor of each node. So balance factor of 12 is 0, balance factor of 8 is minus 1. This is minus 1 because left there is no left subtree of 8. Okay, now balance factor of 14 is 2. The balance factor of 14 is 2 because the height of left subtree of 14 is level 1 and 2 and no right subtree of 14. So overall the balance factor of 14 will be 2 minus 0, 2. Now this tree become unbalanced. So in order to make this tree balanced, we have to recognize that which rotation we need to perform here. Since here 12 is inserted in the right in the left of right subtree of A. It means this is the left and this is the right. So here we need to perform the left right rotation. And what we will do in left right rotation? First we will perform the left rotation. It means we need to rotate the tree in context to 12 in anti-clockwise direction. Okay, here we need to perform this. So 8 will become this and 3 will become this after performing the left rotation. Now we need to perform the right rotation. So in order to perform right rotation, we need to move it in the right direction, clockwise direction. So 12 will become the root and 8 and 14. Now in this case balance factor of each node is 0. So this is a balanced tree. Now we will insert the next value. Next value is 46. 46 is greater than 12. So it will become inserted in the right subtree of 12. Again 46 is also greater than 14. So in the right of. Okay. So after inserting 14, tree will be this. Now balance factor of 46 is 0. Balance factor of 14 is minus 1. And balance factor of 12 will also be minus 1. Okay, because in the because the height of the right subtree is 1 and 2 and height of left subtree of 12 is 1. So balance factor will be 1 minus 2. It means minus 1. Again this tree is balanced up to here. Now we have to insert the next value 23. So when we will insert the 23 is greater than 12. So it will be inserted in the right subtree. Again 23 is greater than 14. So it will be inserted in the right of 14. Again when we will compare here, since 23 is less than 40, so 23 will be inserted in the left subtree of 46. Okay, so balance factor of 23 is 0. Balance factor of 46 is 1. Now balance factor of 14, there is no left subtree of 14 and height of right subtree is 1 and 2. So balance factor of 14 will be 0 minus 2. It means it will be minus 2. Okay, now here the balance factor of 8 will be 0. Again what will be the height of right subtree of 12? So label 1, 2 and 3. So it will be 1 minus 3, it means minus 2. So balance factor of 12 will be minus 2. Now this tree will become unbalanced because 2 node has minus 2 factor. So at first we need to make this tree balance in context to the node 14. Okay, and 14 become unbalanced when we insert in the right in the left of its right subtree. So here in this case we need to perform the RL rotation. Okay, so in case of RL rotation, what we will do, first we need to perform the right rotation. So we will move it in the clockwise direction. So when we move in clockwise direction, then 23 will be the root, will be the parent of 46. Again, balance factor of 46 is 0. This is -1. So this is also unbalanced. Now we need to perform, here we have performed the right rotation. Now we have to perform left rotation. So when we will perform left rotation, then 14 will be moved to downs. Okay, so 14 will here, 23 will here, this will be the 46. Again, balance factor of 14 is 0, balance factor of 46 is 0, 23 balance factor is 0, here is 0, and balance factor of 12 is level 1, level 2 and 1. So 1 minus 2 will be -1. So balance factor of 12 will be -1. Okay, so now this tree is balanced. Next we will insert the next key, which is 5. So 5, we will compare it. 5 is less than 12, so it will inserted into the left. Now 5 is less than 8, it will be inserted in the left of 8. Okay, so balance factor of 5 is 0, balance factor of 8 is 1, balance factor of 12, height of left subtree of 12 is 1 and 2, and height of right subtree is also 1 and 2. So 2 minus 2 is 0. So balance factor of 12 is 0. So when we insert 5, then tree become balanced. Okay. Next, when we insert 77, then it will be inserted here by following the concept of the binary search tree insertion. Okay. Now balance factor of 17 is 0. Balance factor of 46 is -1, because there is no left and right is 1. Balance factor of 23 is -1. Now balance factor of 14 is 0, balance factor of 5 is 0, balance factor of 8 is 0. So what is the height of left subtree of 12 here? 1 and 2. Height of right subtree is 1, 2 and 3. So what will be the balance factor? 2 minus 3, it means -1. So balance factor of 12 will become -1. Okay, now we insert 88. So 88 will be inserted here. So after inserting the 88, balance factor of 88 0, balance factor of 77 -1, the balance factor of 46 will be -2. It will be -2 because there is no in the left or right 1 and 2. Okay, again balance factor of 23 will also be -2, balance factor of 12 will also be -2. This is -2. Okay, and this is also -2. So here in this case 3 node have balance factor -2, 46, 23 and 12. So we need to make it balanced. This is the unbalanced tree. So we make the tree balance in context to at first 46. Okay, so this is the right and right. So whenever 14 balance factor of node 46 is disturbed, when we insert in node 88 in the right subtree of the 46. So here in this case we need to perform the left rotation to make it balanced. So in case of left rotation, what we will do, we will rotate anti-clockwise. So after performing the left rotation on it. Okay, so this will be the tree. So balance factor of 88 0, balance factor of 46 is 0, balance factor of 77 is 0. Now balance factor of 14 is 0 and balance factor of 23 is will be the -1, because left subtree height is 1, right subtree height is 2. So 1 minus 2, that will be -1. Again here the height of left subtree of 12 is 1 and 2. Okay, right subtree height is 1, 2 and 3. So balance factor of this is 2 minus 3, it means -1. So now this is the balance, because every node has the balance factor either 0, 1 or -1. When we will insert 20 will be inserted here. So balance factor 0, 0, 0, 0 and its balance factor is -1. Again its balance factor is 0 because height of left subtree is 1 and 2. Right subtree is also 1 and 2. So 2 minus 2 is 0. Again balance factor of this will become 1. So it will be the balance tree. Okay, thank you.